All right, we're back at it again. So this is intervention number 4, 5, 4. I'm not sure. Can't remember. I don't keep count. Anyway, this is going to be everything to do with nth terms and sequences in we don't know how many minutes. Okay. We're gonna start things off right at the very beginning. Okay. Stuff that you will have done ages ago. We're thinking about linear sequences. We're going to think about what we can do with linear sequences, and then we're going to progress into quadratic sequences. Just so that people know, it is very unlikely that you'll see anything to do with linear sequences on higher tier. It'll pretty much, if you're going to see something about sequences, it's probably going to be quadratic sequences. If you're dealing with something on foundation, it's probably going to be dealing with linear sequences. Very unlikely to be full-on quadratics. And if you're looking at a crossover, well, it's a good idea to have a grounding of both. And it's good to know what you're doing with linear sequences before you're dealing with quadratic sequences anyway. So, this is everything to know about nth terms and sequences, starting now. So the first thing for us to be able to do is to work with just a standard, straightforward sequence. Okay. So I've got a sequence here that goes from 7 to 13, 19, 25, 31. Now, the thing with sequences is that it's always good to see how does a sequence progress. Well, in this case, this sequence progresses by going up by 6 each time. Okay? Now, we need to create that motion of going up by 6 each time. And the other thing that goes up by 6 each time is the 6 times table. Okay. So the first part of our sequence is that we need to have some kind of multiple of 6. Okay. So the first thing, we need to times by 6. Now, if I think of my 6 times table, that goes 6, 12, 18, 24. The sequence that I want goes 7, 13, 19, 25. I need to look, how do I get from what we currently have to what we want? Okay. And to do that, I'm having to add 1. Add 1. Add 1. And you guessed it, add 1. So the second part of our sequence is going to plus 1. Now, at this point, you may have been told, okay, if we times by 6, that means we have 6n. And if we add 1, that means we've got 6n plus 1. But I want to give a little explanation as to why. You're constructing a formula. If you start with an n, and start with your first action in your sequence was to create a 6 times table, you do n and times it by 6. And then add 1. N times by 6, we can write that as 6n. 6n plus 1 is 6n plus 1, which is our nth term. And, you know, if we have a sequence which goes up by the same amount each time, we can do that with our sequence. Even if it's going down the same amount each time, we can still do exactly the same. Instead, our times table will be slightly different. Just like this one here. This one isn't going up the same amount each time. It's going down the same amount each time. To get from 3 to -1, I have to take away 4. From -1 to -5, I have to take away 4. From -5 to -9, again, I take away 4. So by subtracting 4 each time, that's the same as us doing our -4 times by table. So the first part of our sequence is to times by -4. What did we do after that? We checked what the -4 times table looks like, what we have. Well, that would be -4, -8, -12. But I don't want that. I want that to be 3, -1, -5. And how do I get from -4 to 3? Well, I add 7. How do I get from -8 up to 1? I add 7. So that means that the second part of our sequence means that we're going to be adding 7. So then our nth term is going to be made by taking n, timesing by -4, and then adding 7. It's going to give us -4n plus 7. And that is an nth term for a linear sequence. Okay. All right, so you might have found out your nth term, but you might be also thinking, well, what do I need to use that for? And the whole reason we come up with rules in maths is to make prediction. So we could be asked, I've got this sequence which starts off going 7, 13, 19, 25. I want to know, is 125 in that sequence? Okay. So let's have a look at that. Oh, hang on. So I have a sequence that went 7, 13, 19, 25, like that. Is 125 in that sequence? Now, we can't just offer up yes or no and be done with it. We need to give some kind of reasoning. Well, we found out that the nth term for this sequence that we did previously was 6n plus 1. Okay, we might say that that is our nth term, and you might see notation with t with a little n, meaning nth term. Now, if 125 is in that sequence, then at some point, 125 would be equal to 6n plus 1 for some value of n. We don't know what that value of n is. If we can find out that that value of n is a whole number, then it is in our sequence. So if n is whole, that's a yes, and n is not whole, then no, it's not in our sequence. Okay, and you will have solved equations like this like time and time again. I shouldn't have to go out of my way to say what this is. But what we eventually find out is that n is 124 over 6. Now, my mental arithmetic would tell me that 124 does not divide by 6 to get us a whole number. Okay, 120 would. That would be 20. But 124, no, it's not an integer, not a whole number. So 125 is not in our sequence. Shock horror. Okay. So that's one thing that we might have to do with an nth term. We might have to make a prediction or tell someone whether a prediction is right or not. We could also be asked, what's the 40th number in this sequence? What is the 50th number in this sequence? And if that's the case, we would just have to say, okay, what does our sequence equal if n is equal to 40 or n is equal to 50? Because what n represents in our nth terms is a particular number in that sequence, okay? It could be the 5th number or the 7th number, okay? But t with the little 7 would be the 7th term, okay? And then I would just say, what is 6 times 7 plus 1 for the 7th term, okay? So that's something else that we could do with a linear sequence, okay? Now, I've looked to try and get through that relatively quickly because it's going to take us a little bit more time for us to talk about the quadratics. If you want to practice the linear sequences part of things, this type of skills that I've looked at there, this kind of these questions here will do that perfectly well. Okay, you've got finding nth terms with fractions, nth terms with decimals, and you've got a cheeky little tell me what the third term is there at the very end as well. Okay, but the rest of this video, and what I encourage most of you to be looking at, is the quadratic sequences, which is what comes next. All right, so quadratic sequences. I'm going to take this a little bit slower, okay, because this is the thing that typically trips people up, okay? The linear sequences, not so much, but we need to have a little bit of an understanding of our linear sequences for us to know what's going on with our quadratic sequence, okay? So, when working out an nth term for a linear sequence, what we did first was to see what our sequence goes up in. And, well, for 3 to 6, that goes up in 3. From 6 to 11, that goes up in 5. And then 11 to 18, that goes up in 7. And then that goes up in 9. So this is constantly changing. But you can see a pattern for those numbers. And if you remember to when we did this in class, we need to also check the difference of those numbers. Okay, and if I do that, this number here, if I take that number and divide it by 2, I will get my coefficient of n squared. Okay, coefficient is just a posh word for the number in front of. So if I take this number here and divide it by 2, I get the number in front of x squared. 2 divided by 2 is 1, so I end up with 1n squared, which we don't need that one there, so let's get rid of that. Now, for this sequence here, I need to think about what do I do next. If we look back to our linear sequences, we find out what we were going up in, or we found the first part of our sequence, and then we looked at what did we need to add on, what did we need to take away. So I need to think about what do I need to add on and what do I need to take away. Now, for this kind of a sequence, I need to do a little bit more work for that. Okay, I need to think about my term numbers. So my first term is 3, my second term, which is 6, my third term, which is 11. I'm going to go up to my fourth term, which is 18. Okay. Now, n squared, that's the first thing that I'm looking at. Okay, so I need to think out what is my number, my term number squared. Well, 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. But we don't want that. That's what we're starting with. what we want is 3, 6, 11, 18. Okay. Same kind of idea that we used for our linear sequences. It's just it's a bit harder because we needed to think about what n squared was rather than just a times table. Now with n squared sequences, we might need to do a little bit more work with this. So we need to check multiple terms. We can't just check the first one. So with this one, I have to add 2. From 4 to 6, I would add 2. From 9 to 11, I would add 2. This looks good. And from 16 to 18, I would add 2 as well. So my nth term that I'm going to have for this, my nth term of my sequence, is going to be n squared, because that was the first part of my sequence that I knew that I had from doing this bit up here, plus 2. The bit that I knew I had to add on to get the sequence that I wanted. Okay, and the bit that I remember people being least sure about when we first did this was this stage in the middle. Okay, now, if you weren't 100% with that, I'm going to be showing an alternate method after this second example, which might make your life a little bit easier, okay? This second example, same kind of idea we're going to use, slightly more tricky, okay? So let's get our color blue back for the starting thing. I need to check my differences. So 9 to 14, that goes up 5. 14 to 25, that goes up 11. 25 to 42, that goes up 17. And then 42 to 65, that goes up 23. Again, sequence doesn't go up the same amount each time. I need to check my second differences. 5 to 11, we go up 6. 11 to 17, we go up 6. 17 to 23, we go up 6. Divide it by 2 to get our coefficient of n squared. So 6 divided by 2 is 3. I'm going to get 3n squared. That is the first part of my sequence. I need to look at my term numbers. 1, 2, 3, and 4. The first part of my sequence goes 3n squared. Now, I'm just going to make this a little bit more explicit. I'm going to say 3 lots of n squared. That's what that means. It's the same thing. So, n squared. 1 squared is 1. Times it by 3 is 3. 2 squared is 4. Times it by 3 is 12. Okay. 3, my third term. 3 squared is 9. 9 times 3 is 27. Fourth term, 4 squared is 16. 16 times by 3, that is going to be 48. All right. Now, let's have a look. I don't want this sequence here. This is my starting point for the sequence, but it's not the sequence that I want. I want the sequence that goes 9, 14, 25, and then 42. Okay, so let's have a look at what's going on here. To get from 3 to 9, I would need to add 6. To get from 12 to 14, I would need to add 2. Oh, all right, okay, let's check what's going on here. 27 to 25, I would need to take away 2. 48 to 42, I would need to take away 6. Now, this is where it gets interesting. I wonder if you can guess what I'm going to have to do now with those numbers there. The ones that I'm about to shade, put circles in red around. We are going to have to find out what's the linear sequence for those numbers. Okay? So I need to know what is the nth term of 6, 2, -2, and -6. Well, 6 to 2, we take away 4, take away 4, take away 4. Okay, and this part should be a linear sequence. If this is a quadratic sequence as well, something has gone wrong. Okay. My -4 times table, like that, but I want the sequence that goes like this. To get from -4 to 6, I need to add 10. From -8 to 2, I add 10. And from -12 to -2, I would add 10 again. So this linear sequence is going to be -4n plus 10, which means that my overall sequence is going to be 3n squared from what we had before, this bit up here, and then tacking this bit on at the end. Now I realise that at this point, with me sitting here in my chair at home, like recording this video, that these stages here are not always that obvious, because you have to be looking at how you want to get from the sequence you've currently made from doing this stuff at the top to the sequence that we want. And because that amount keeps changing, it's very easy for you to think, oh, I must have gone wrong somewhere. But we haven't. Okay? It's then we need to check what the nth term of that sequence is by doing what we would do for a linear sequence and then tacking it on the end. Now, I will admit that when I went through school, this is how I learned it. Okay? And when I did my teacher training, this is how I learned it. And how I taught it to other people. And it was only when I started marking exam papers that I saw that there was a different strategy. Okay, and this was, 2 or 3 years ago. Okay. Now, what I'm going to show you here is an alternate strategy, which is a bit more procedural. Okay, it's and I think some might say it's a bit easier to follow. Okay, so we're going to take a look at this, and then we're going to see. I'm going to give you some chance to practice, okay, and see where we go from there. And I might going to have to explain what's going on here a little bit, so please bear with me. We know that any quadratic equation can be written like this. Okay, any quadratic equation can have some squared parts, some not squared parts, and then add or subtract something at the end. Okay. We could have -2n squared plus 5n plus 1. Okay. Any quadratic can be written like that with some letters for A, B, and C. So numbers for A, B, and C. What we want to do for our alternate method is to see what values we get, or what expressions we get for this generic quadratic. So what happens if n is equal to 1 for our first term? Okay. Well, if n is equal to 1, I've got 1 squared, which is 1, times a. Well, 1a is just a. Plus 1 times b is b, plus c. What about when n is equal to 2? Well, when n is equal to 2, I would have 4, because 2 squared. I'd have 4a plus 2 times b, 2b, plus c. And for when n is equal to 3, I would have 3 squared, which is 9a, plus 3 lots of 3 lots of n. I really need to get my words right. 3 lots of b, I was right the first time, plus c. You might think at this point, well, hang on, how is this going to help us? This just looks worse. This is just more and more algebra. Hang on. What is the change from our first to our second term? Well, we got 3 more a's and we got 1 more b. What was our change from our second to our third term? Well, we got 5 more a's and 1 more b. Now, we saw for our quadratic equations on our previous examples that we needed to find a second difference. So what's the difference between these two things? Well, we got an extra 2 a's. Now, this explains why we needed to divide by 2 to find out what our number in front of the n squareds was for this thing here. Okay, that's why. Now, why does this method perhaps give us a little bit more help? I know that the first number in my sequence is going to be the same as a plus b plus c. I know that the first difference is going to be the same as 3a plus b. And I know that the second difference is going to be equal to 2a. So let's see if we can use that information for the sequence that we did earlier. So, first difference between 9 and 14 is 5. 14 and 25, our difference was 11. And our second difference was 6. So I know from comparing it to our generic sequence above that 6 is equal to 2a from right at the very bottom. I know that 5 is equal to 3a plus b. And I know that 9 is equal to a plus b plus c. Now, if I know that 2 times something is 6, I know that a is equal to 3. If I know that, then that means that 5 is equal to 3 times 3 plus b. If I know that, then that means that 3 times 3 is 9. 5 take away 9 is equal to b. b is equal to 5 take away 9 equals negative 4. If I know that, then I know that 9 is equal to 3 plus negative 4 plus c. Well, I know that 3 add -4 is the same as 3 take away 4, which is -1. So I know that 9 equals -1 plus c. And I know that that means that c is equal to 10. And when I put that back into my generic quadratic, I know that a is equal to 3, so that's going to be 3n squared. I know that b is equal to -4, that's -4n. And then that c is 10. And that is the nth term of our sequence. Okay? If we jump back to our previous slide, completely different workings, like completely different, but exactly the same answer. Exactly the same. Okay? So you've got 2 very different methods for quadratic sequences. I think that this links slightly better to what you do with linear sequences. I think that this can work well as a like one size fits all strategy. And if you understand what's going on there and you think that you can construct these different expressions in the middle of an exam, then this is absolutely a good method to use. However, I personally, and it could just be because it was what I was taught at school myself, I feel that this has a little bit more nuance to it, perhaps a little bit more you require a little bit more understanding for this. Okay, so that's my half-an-hour video. I'm gonna try and stop it there. You've got now 2 things that you could look to do. You've got your linear sequences, which most people here should be absolutely fine with. Okay, I would expect that most people should not need to have a look at this. And then there is a worksheet which I've also put into Teams, into the folder, which deals with quadratic sequences. But I want us to focus on specific questions. Okay. So I'm going to get the worksheet up on my other screen here. So the questions that I want us to look at from the worksheet are question 2, question 3, question 7, and then if you're looking for, I will go for question 8. And if you're looking for a real challenge, I would say go for question 9 and question 10. Make that slightly better. There we go. I would say that those will kind of challenge the skills. And if you want something which is a little bit different, go for apply question 2. Okay, those will still do exactly the same skills, but the setup is slightly different because you're dealing with pictures rather than just straightforward number. Okay. I am expecting people to watch these. I am expecting people to get involved with some of the questions as well. And if you do have questions, email me them, see me after lessons, whatever you need to be able to do them. Okay. Right. Go and do the thing. Go on. Go on, off you go. There's no point listening now. There's no more. We're done. See, look, if I press the next slide, there's nothing here. The end of the slideshow. Go and do the work. Go. Off you go. Don't know what you're waiting for. I'm just going to wait. Fine, I'll stop.